All right, so let's start. This last chapter of the course about talking about three-phase converters. So let's start with some introduction. We need these things for some of you who are not familiar with, or even if you have seen that, will be review and also becoming familiar with the notations that I'm going to use. Symmetrical components, or also called sequence components. Basically, we have positive sequence, zero sequence, negative sequence, and zero sequence. And remember, it's AC, three-phase AC at a given frequency, for example, 50 hertz or 60 hertz. So positive sequence, a positive sequence waveform is like this: three sinusoidal function with the same magnitude, same frequency. Phase angles of the phase B is 120 degrees behind phase angle of phase A, and phase angle of phase C, waveform C, is 120 degrees behind phase B. So it's called phase A, phase B, phase C also. Negative sequence is very similar with the difference now that this 120 degrees is advanced. So I use XP, P for positive, CP, C for cosine, so they use cosine functions. You can use sine also, but you have noticed cosine seems to be more convenient for these discussions. Theta P for positive sequence angle, theta N for negative sequence. And theta is omega into t plus delta. This is the initial phase angle at the time 0 that you assume that time 0. How much is the angle? And omega is the frequency. And zero sequence is this. Same magnitude, same phase. All the angles are equal. Okay. So there is a theorem, and that theorem really is not difficult to prove, that says any three-phase waveform, XA, XB, XC, that have the same frequency and sinusoidal, you can decompose it into a positive sequence plus negative sequence plus a zero sequence. Okay. So we notice that positive sequence, because they have 120 degrees phase shift with each other, if you add them together, become zero. For the negative sequence also, they become zero. So if you add together all these three, this one and this one and this one, the positive parts become zero, the negative parts become zero, and then the zero part, the zero sequence parts, they add together, so become 3 times the zero sequence equals XA plus XB plus XC. So zero sequence you can easily calculate for any given waveform. If you have a three-phase waveform, you just add them together, divide by 3, that gives you the zero sequence. Okay, unbalanced factor. So in practice, ideally, in power system, we would like to have only positive sequence. If you have negative sequence, you can define the amount of negative sequence to the amount of positive sequence as unbalanced factor. You can bring in zero sequence, but normally you only talk about negative sequence for the unbalanced factor. Powers. How do we calculate the powers in a three-phase system? Okay, so this is a simplified diagram of a three-phase source that is connected to a three-phase load, right? Let's assume that there is no neutral connection. right? So if there is no neutral connection, then IA plus IB plus IC is 0, according to this Hearn law. And if that is 0, that means that if you fictitiously, so to speak, connect this, let's say, this point to this point, and again this point to this point, and this point to this point, you can say IA runs here, IB runs here, IC runs here. So you have now 3 circuits, one here, IA, and then you have B here, running here, and also C. And then because IA plus IB plus IC is 0, you haven't done anything wrong. So what it means that you can break it down, this 3-phase system, into 3 single-phase system as far as the power is concerned, power transfer is concerned. And then you can say the instantaneous power is instantaneous power of the first circuit plus second circuit plus third circuit. For the first circuit is VA-IA, for the second circuit is VB-IB, for the third circuit VC-IC. In terms of vector notation, you can say V transpose into I. So we consider vectors column vector. When you transpose that, it becomes a row vector. So a row vector into a column vector, that basically gives you this one. So complex power we already defined for single phase. Here for 3-phase, you will add them together, and then the complex powers, they will add up, no issues. In a balanced situation, voltage and current, if they are balanced, both of them are positive sequence. Let's say V is positive sequence, I is also only positive sequence, right? Then P becomes constant. Instantaneous power in this equation becomes completely constant. So you will have no double frequency ripple. And this is really the big advantage of a 3-phase system. And I would say the reason that we use 3-phase system. Because 3-phase system will have no double frequency ripple if it's balanced. But single phase system always has 100% ripple, because it has an oscillation which has the same magnitude of the DC. But here you do not have any ripple. And then the real power is this one, the reactive power is this one. So 3 times the single phase real power, 3 times the single phase reactive power without any pulsation. This is a fantastic situation. It's a very interesting situation. If it's unbalanced in general, let's say voltage is this, current is this. So current does not have 0 sequence because we assume there is no neutral connection. And then when you multiply them together, and there is a little calculation here, I said you can do as an exercise, you will see a constant term that we call it real power again, and then some double frequency terms. So double frequency terms appear when the voltage and current become unbalanced. But the magnitude of that unbalance depends on the negative sequence of the current or negative sequence of the voltage, which should not be huge in the normal operations. Okay, space phasor, remember in one of the earlier classes we already defined it for a 3-phase system, alpha, beta. And then space phasor of a 3-phase balanced positive sequence waveform will be this one, x into e to the j theta. Now I'm going to introduce several notations. It may sound a little complicated at the beginning, but as you go on, you will see how much they will help with the analysis and design of the 3-phase systems. So this e to the j theta, which is cosine of theta plus j sine of theta, I'm going to call it SDP. D for direct, P for positive of theta. Okay. And this equation, if you look at this equation, is a complex equation. So all the time when we have equations of this sort, you have options of either showing it this way as a complex equation, or you have option of putting them, the real part in here, the imaginary part here, and show it as a vector. Some people like vectors, some people like complex notations, doesn't matter. They are equivalent. So vectors or matrices, or just working with the complex quantities. If you go with vectors, that will be this one, and SDP now becomes this, a vector. Either this or this. These are equivalent. This is, you can say, is a complex vector. This is a real vector. Now, if it has a phase shift, already a phase shift delta, then it's a space vector, space phasor, will have this component SDP and SQP. And SQP now is e to the j theta minus 90 degrees. So Q for quadrature, always quadrature with respect to direct has 90 degrees phase lag. So you see negative 90 degrees here. Okay, so that's a common, that's a consistent way that I will go with quadrature and direct. And in terms of real vectors, that will be this one, we already said, and for Q will be this one. So this was basically what is the expression of space phasors for a positive sequence. For a negative sequence, you can also derive. If you have a negative sequence waveform, and then you calculate its space phasor, that gives you this one, which is now negative theta. And I'm going to call this SDN, direct negative, right? And in terms of real vector will be this. And if it has a phase shift, it will have two components, SDN and SQN. And SQN again has 90 degrees phase shift with respect to SDN. So SQN is 90 degrees behind SDN. Summary. In these two equations summarizes everything, basically. You define these four vectors, SDN, SDP, SQP, SDN, SQN, either in complex or in real domain. So extension of the concept of complex power to three-phase is basically done using space phasors. So it's 3/2 space phasor of V into space phasor of I conjugate. And then this complex power has a real part, which is the real power, and an imaginary part, which is reactive power. And voltage has a real part, we call it alpha, an imaginary part, which has beta, and the current also has a real part, alpha, imaginary part, beta. If you put it here and do the multiplication, you come to these two very important equations, V alpha I alpha plus V beta I beta into 3/2 for P, and V beta I alpha minus V alpha I beta for Q. Okay. Now again, in this domain, if you look at the real power and reactive power, if it's a balanced situation, you get to the same point that we discussed before. For P, you will get 3/2 V into ID, and for Q, negative 3/2 V into IQ. And if it is unbalanced situation, let's say VA is this, IA is this, only for phase A, showed the values. Then space phasor for V and for I. So V is taken as reference, so only has direct terms, but current has direct and quadratures. So direct minus quadrature here, and again direct minus quadrature here. And then if you multiply them together, V into I star, and then really put all the terms with the angles and do the simplifications, you find eventually a bunch of constant terms and a bunch of terms that have double frequencies. You see, double frequency, and this is again constant, constant. So all those constant terms merge together, right? Plus double frequency, real parts. So all that are real parts, regardless of constant or double frequency, now put them together, that gives you the real power. And all the complex parts, put them together, they have some constant values and some double frequency values. That gives you the reactive power. So I think this is still, yeah, reactive power is here. So the conclusion is, if you really look at these terms, as long as expected, as long as the system is balanced, we only have DC real power, DC reactive power. When it becomes unbalanced, we have double frequency ripples on power, real power, and also on the reactive power. And the expressions for the double frequency ripples of the reactive power and of the real power are exactly this. This equation tell you how big is the pulsation, and these parts tell you how much is the DC part or the constant part. This is basically the amount of actual power which is transferred. The other part is double frequency, so it's pulsating. And this is the amount of reactive power that is exchanged. This one is pulsating. Okay, now if you look at these equations, because we are going to work with these equations, and in these equations, several parameters like Vp, Ip, Vn, In, IDQ, IDN, IDP, IQ, P, IQN, all these parameters appear. These are the positive sequence and negative sequence components of the voltage and current. So we constantly need them. And again, and also the angles, even more important than the magnitudes will be the angles, theta P, theta N. These angles, we need to work with them in control. So we need to have a mechanism like single phase to estimate these angles and these magnitudes for us. Over there we used PLL, here also we use PLL, but it's a little bit more extended. So this is a conventional, called it synchronous reference frame phase lock loop, which is used, slightly modified here in this presentation, but not much. So there is an ABC to DQ transformation, which we talked about before, and it gives you D component and Q component. You filter the D component, which estimates the magnitude, and you divide the Q component by this filtered version. So this is now a normalized version of the Q component. So it has the information of the angle difference in it. And then if you regulate that to 0, and by regulating it to that 0, generate an internal variable for frequency and integrate that again to generate an internal variable for angle. If this loop is stable, you can prove very easily that this angle will converge to the angle of the positive sequence of this waveform. And this frequency or this variable will converge to the frequency of this waveform. And this UD will converge to the magnitude of the positive sequence of this one. So in other words, this simple algorithm, if it converges and has no stability issue, in one shot gives you an estimate of the magnitude, frequency, and angle of the positive sequence of this waveform. So this is ABC to DQ transformation, just a little analysis. And this is UD, this is UQ. So you see when theta, assume theta goes to phi, then this goes to the magnitude because cosine becomes 1. Now if theta goes to phi, this goes to 0. So basically we push this to 0 using a control loop, a feedback loop. We push this to 0 using a feedback loop. And then when you push this to 0, theta has to go to phi. And then when theta will go to phi, UD will go to capital U. Approximate linear analysis. This is for the sake of design of the parameters. This circuit has 2, or you can say 3 parameters, mu1, mu2, mu3, like a single phase PLL that we discussed yesterday. So for the design of mu1, mu2, mu3, you can go to a simple linear analysis, and then you derive a transfer function or you derive a characteristic equation. And by comparing this characteristic equation to a standard second order equation, you will find how much is mu1 and how much is mu2. So you have a damping ratio and a natural frequency, which you need to choose. Damping ratio, you know what are the criteria for choosing a damping ratio. And this omega n represents the bandwidth of your PLL. So you choose them, and then by choosing that, you calculate mu1 and mu2. An alternative presentation of the PLL that I just mentioned is this one. This is the same PLL, but with the different notations. Basically, it uses CP and SP. CP is a cosine function, vector cosine function, as we discussed. And SP is a vector sine function. And then you calculate these vectors and then do a dot product. Dot product means transpose of one vector to the other vector. So you multiply them together. So it's completely straightforward to see that this diagram is exactly identical to this diagram. Because this ABC to DQ transformation is actually has 2 rows. So one of the rows come here, one of the rows come here. Okay, so now that I have this one, I'm going to go one step ahead, and this structure basically does the same thing in alpha beta domain. So it says, let me first convert ABC to alpha beta and then alpha beta to DQ. Okay, that's the same thing, no problem. Now, this structure, what it does, it says, once I have alpha beta at this point, I'm going to add this part as well. So it's a subtraction of alpha beta minus this SDP that is calculated from PLL multiplied into the magnitude, which is calculated here. So this signal will converge to this one, and this becomes 0. So this is the first enhancement to this PLL. So we call it enhanced PLL. And the idea is taken from, again, the single phase, but you can initially take from 3 phase, no problem. Because in single phase, the ripples are there. And if we added this subtraction to remove the double frequency ripples. In 3 phase balanced situation, the ripples are not there. So even if you add this subtraction, it's not going to help it anything. It's not going to change anything. We have no ripples. But you will see now we are going to move to the next case that we have negative sequence. If you have negative sequence, you can use this summation here. But before going to that point, let's do a little analysis of this basic EPLL. Because of this subtraction, it gives you some nice properties mathematically. For instance, again, if you choose this mu1 equal to mu3 and choose mu2 equal to 0, right? You can prove that with this arrangement, the entire system becomes linear time invariant. That's basically what this theorem says. So in other words, this arrangement and under these conditions reduces the PLL to a completely linear time invariant system. So you can say basically it linearizes the operation of the phase lock loop. And this is the proof. You derive the equations and then you make a change of coordinates and eventually you prove that your equations become linear time invariant. And then when they become linear time invariant, you can derive a transfer function for the phase lock loop. Well, this transfer function was never derived before because this transfer function, remember, it's not based on small signal or anything. We did not do any small signal. Always people in engineering, when there is a nonlinear equation, they want to derive a transfer function, they linearize it. They find an equilibrium point, operating point, small signal analysis. That's a but we did not do that. We just manipulated the equations, added things, put some conditions on the parameters, and then we said in large signal, this system is linear. Not in a small signal. In large signal, this system is linear with these transfer functions. We only put two conditions, mu1 equal mu3 and mu2 equal 0, which means if you are really operating in a tight frequency regulated situation. So based on these discussions that we had, you can design mu1, mu2, mu3. Because now that you have this transfer function, this gives you the poles of this system. So again, put that equation, correspond that equation to a standard second order system which has a zeta and omega n, damping ratio, and the natural frequency. And from there, find mu1, right? So find mu1 from this equation, can approximate that, and then mu2 and mu3 is equal to mu1. Okay. This theorem we don't need. Now let's move to the case that we have a negative sequence. If we have negative sequence, now you see the benefit of having this summation here. I will add another component here. That component comes from this block. And if you look at this block, what is this block? It's the copy of this block with only changing SDP to SDN, SQP to SQN, frequency, the same frequency from above, right? And these blocks here, and then I calculate this Y, VD, multiply into, and then I bring this and add it here. So this block estimates the negative sequence, this block estimates the positive sequence, you add them together, and then subtract the entire thing from this one. So the errors will not propagate, and eventually you will have a perfect decomposition of this signal into positive and negative sequence. Okay. All right. So, and again, under this simplifying assumption, you can derive a linear time invariant set of equations for this entire system. It's not difficult. So you have two equations for the positive part, right, and two for the negative part. You can combine them together. You get four equations. You can find the matrix A for this. Eigenvalues of this matrix will show the poles of this PLL. And if you calculate that, you will see the eigenvalues are repeated. Same eigenvalues on the positive sequence, same eigenvalues on the negative sequence. And then, again, you derive a simple algorithm for the design of mu1 and mu2 for this system. Mu3 is the same as mu1. This algorithm is significantly important, but at the same time simple. And if you look at it, it's exactly the same algorithm that we had for single phase EPLL, with the difference that in the single phase, this number 4 was 8. Here is 4. Otherwise, everything else is exactly the same in this and the other one. So the numbers I have explained here. Now, DC, we said before, is important in PLL. We don't want to ignore that. If you want to handle DC, you need to add this branch. So you take the error. So if there is a DC here, that DC comes here. So you take that DC, integrate it, bring it back here, and add it to the negative sequence. So now the DC, the negative sequence, and then come here. Remember, zero sequence doesn't matter, because zero sequence, whether it exists or doesn't exist, it will not come to alpha beta. So we don't worry about zero sequence. But we worry about DC because practically, we explained before, it may be generated during the signal conditioning and processing, signal processing stage, even if the original signal doesn't have DC. Now, again, this is a linear part, linear thing. So if this is linear, this is also linear, we said, under mild conditions, and this is linear. Now you can derive the equations, linear equations for the entire thing. And they will give you a matrix 6 into 6. So this PLL will have 6 eigenvalues. And I was not able to derive an equation for the eigenvalues of this matrix, so I plot the eigenvalues, I guess, isn't it? Yeah. So if you look at the parameters, here is mu1, right? And mu0. So let me say how I proceed. Choose the damping ratio zeta and calculate mu1, okay, the same way we did before. Choose the damping ratio C and calculate mu2 as before. Now, once you have mu1 and mu2 in this matrix, you can change mu0 and look at eigenvalues of this matrix. So sketch the root locus of eigenvalues of A to find mu0. Typical graph that you will see when you increase mu0 from 0 all the way, you will see there are 6 poles, but they are on top of each other. So 2 of them will move here, 2 here, 2 here. You need to stop somewhere. Where? My recommendation is increase mu0 until all 6 poles have almost similar or equal real part. Then you will get some good responses. If you stop before that, you have some slow responses. If you stop after that, you may have faster responses but more oscillations. So this seems to be a good trade-off, but I cannot prove it. So for instance, for the numbers that we just had, mu1 will be 188, mu2 will be 5,600, and mu0 will be 100. Okay, so that was a brief discussion of the PLL for 3-phase. Now we go back to the problem of inverter control in 3-phase. So what is the problem? Statement of the problem: we have a 3-phase inverter connected through a 3-phase inductor to a 3-phase AC system, either grid or load. And on the DC side, again, there are some batteries or other assets. This is a simplified diagram, basically. So the starting problem, the starting case would be, let's say this is a grid, AC grid, stable. And here again is a DC side stable. I would like to control the amount of power that flows from this DC to this AC. Or even if it's bidirectional, back from the AC to DC, no problem. So both inverter and rectifier. So we use, as we said before, we use PWM, right? And these are the models that we have. And we said we have three equations, A, B, C. You can convert it to alpha, beta. You get two equations. We discussed all these things, if you remember, in the first or second class. And then eventually the controller structure will be like this. You have two loops, one for alpha, one for beta. So I alpha reference minus actual I alpha, a resonant controller, two gains, and then one state variable here, that is the current, bring it back. There is a feed forward term coming from PLL, and this is the input linearization. So inverse of this comes here, and that's it. So this is for alpha and another one for beta. If you want to show both of them together, this is how it works. You take I, and this shows the complete diagram of the controller. So you measure the current, and then you measure the grid voltage. The grid voltage goes to the PLL, and then PLL gives you SDP and SQ, SD and SQ, P and N, and feed forward terms that you need here. And then you convert ABC currents to alpha beta, right? And then multiply into these gains that you calculated, K3, and then K1 and K2 that you calculated here. Eventually you find U alpha and U beta divided, multiply into 2 over VDC gives you M alpha beta, convert it back to ABC, and then give to the PWM. So that's and the reference current, which we are going to discuss, is calculated based on the set point of real power and reactive power. So this is the controller in the stationary frame, right? We did not go to synchronous rotating frame. This is the controller in the stationary frame, and we used resonant controllers. And resonant controller, you know how it is. We discussed that in detail before. And the equations of the resonant controller and the design of the controller based on this. In other words, for alpha and beta, each one of them is a single phase. And we have done this before in details. Now let's talk about reference generation and limiting, how we do that. If it's a balanced situation, that means grid voltage is balanced, right? And you only have positive sequence. What's this expression where VGP denotes positive and negative sequence? I think it has both of them here for some reason. Starts with general expression. So I derived the expressions again one more time. It's not necessary. Oh, the voltage, okay. The voltage I consider, the voltage is the grid voltage. When I say balanced here, I mean balanced current, yeah, to be specific. I forgot that. So what is this situation? This situation says, I want my converter to generate balanced current, regardless of whether the grid voltage is balanced or unbalanced. So the grid voltage has, in general, a positive sequence and negative sequence, right? The current here only has positive sequence. In other words, I want the converter to generate positive sequence balanced current, and grid voltage could be balanced or unbalanced. In this scenario, if you calculate the complex power, you will see that it will have real power, which has pulsating term, and reactive power, which has pulsating term, if the grid voltage is unbalanced. So If the converter generates balanced current and the grid voltage is also balanced, everything is good. Power, real power is constant, reactive power is constant. If the grid voltage is unbalanced, real power will have pulsations, reactive power will also have pulsations. Okay, and then you can calculate the reference from these equations that we just derived. You want this to be the real power, so this will be the real power, and this will be the reactive power, the set points. So these are given to you. This amount of real power, this amount of reactive power, put it equal to this one, find ID and IQ, and then come put it in this equation. So you find ID, you find IQ from the set points of real power, reactive power, and then put into in this equation. You calculate the reference. What about limiting? You need to limit ID and IQ. This is the way to do it. And we have already done this before. So you generate ID and IQ. You calculate magnitude of the current, entire magnitude. You limit it. Now this limited value you multiply back into, right, this one. And then so these currents here are limited now by the limit here. And then you multiply into SDP, and this SDP is a vector. Remember, it has two components, and SQP has two vector. And then you do this subtraction, that gives you the reference. So this reference is sinusoidal to alpha beta, and it has this property that its magnitude never goes above the saturation limit that you put here. If you want your converter to also feed unbalanced current to the system, then the current can be, this is the positive sequence part, and this is the negative sequence part. Now, if you calculate the power, this expression is a little big, but finally you will see that real power will have, again, a DC and a pulsation, reactive power also a DC and a pulsation, right? And this DC should be equal to your set point. This part also real power set point, and this should be equal to reactive power set point, right? But now you have some degree of freedom because you have positive sequence of current and negative sequence of the current. You can use that degree of freedom to make this this pulsation 0 if you want, or this one 0, 1 degree. You only have 1 degree of freedom on top of these two set points. So I have discussed that in some details here. So this equal to P set, this equal to Q set. And then if you want to put that repels to 0, for instance, it will end up these conditions. So you choose IDP equal to this and IQP equal to this one, IDN equal to this one. This basically, this satisfied real power set point, this satisfied reactive power set point, and these two together satisfy that the pulsations from the real power are removed. So your real power becomes smooth and constant. And then finally, your reference is this one. And this diagram shows how to limit the current. It's a little complicated. And one aspect is that I have mentioned in the text, I don't want to go into detail. The current limiting, especially in unbalanced situation, is a challenging problem. This manages to do to a certain extent, but it's not perfect. You will see in the simulations. And still, I think there could be more research done to improve the results here. The parameters that are used for simulation in this chapter is 500 volt DC as before. On the AC, we have 3-phase, 120 volt, 60 hertz. And 2 millihenry for the inductance, 4 kilohertz switching frequency, 10 kilowatt power rating, plus minus 10 kilowatt reactive power, and current we want to limit at peak value of 70 amperes. So the rated current at full load condition is 55.6 amperes, but we would like to limit at plus minus 70. The design of K1, K2, K3 we have already done before. The same diagram that we had in single phase because it's the same system. In alpha beta, the good thing is that these channels are separated. So the same design that we had in single phase, you can use it here. So look at some simulations here. So in this one, obviously at the beginning is the time that PLL is working until 50 milliseconds. And then after PLL converges, you start the converter. There is very soft and a smooth start. And at this point, real power set point of 10 kilowatt applies. And the converter immediately starts generating the current. And the power goes up to 10 kilowatt. And then here you have reactive power jump. And the converter follows. Reactive power back to 0, back to negative 10, and to 0. Here is the grid voltage fault to check the current limiting property, which successfully is done. This is the case that the current is balanced. So if you look at the current waveform, it's completely balanced. This is the current waveform, and this is the grid voltage. This situation, you immediately see when the grid voltage is unbalanced, but the converter still supplies balanced current. So the converter supplies balanced current, but the grid voltage is unbalanced. So the real power, as far as the average is concerned, is follows, no problem. Reactive power too. But there will be pulsations. Both real power and reactive power will have double frequency pulsations. This scenario is because when you say here, when I said voltage drops, all three phases drop equally. In three-phase system, this may not be the case. They have different situations. For instance, maybe one phase drops to 0, two other phases do not change. This is single phase to ground fault that happens. So I check that situation separately. So grid voltage is balanced, the current is balanced, a deep single phase to ground fault happens. During fault, the current should be limited. It's not even reaching 70 amperes. But there is huge amount of pulsations on real power and reactive power because it's extremely unbalanced, right? So you will get a lot of pulsations. This is a more severe fault that two of the phases go to 0, one phase does not change. So, and then you will see larger pulsations, double frequency pulsations on the real power and reactive power. But the converter's operation is perfectly fine. This is the situation that we allow the converter to generate unbalanced current when the grid voltage is unbalanced and also remove the pulsation of real power. So the voltage is unbalanced, the current is also unbalanced, the real power has no pulsation, but reactive power has pulsation. And you can see that when we remove the pulsation of the real power, the reactive power's pulsation become a little larger. This is some extreme conditions. All the time when you design a controller for a system, make sure you test all extreme conditions if you want to really prove that your controller works. These extreme conditions, I think I explained in the text. Basically, look at the parameters of your system, push them to the limits. and then see if the controller can tolerate them. The inductances that you have, let's say the inductance you assume 2 millihenry. Now push it to 3 millihenry in your simulation. Don't change the design, but just increase the inductor. Or there is an inductor connecting the terminals of the converter to the actual grid. We call it grid impedance. That is also a great point for uncertainty, the grid impedance. So I think here it says a grid impedance of 2 millihenry is added to weaken the grid, and the inductance of the filter, which was 2 millihenry, is increased to 3 millihenry. So that's the extreme condition, and you see the responses are stable. There is a slight differences, slightly more oscillations in terms of powers, but still can hold together. Okay, let me very quickly, if the file open, yes, go through the file as well. Okay, the power circuit, now a three-phase inverter, voltage source converter. We have a DC voltage here, which I put a step function so I can apply disturbances if need be. On the AC side, we have a filter, three-phase filter, and this is point of connection. And then we have an impedance that models the grid impedance, and this three-phase voltage really models the voltage behind the impedances. And these controllable voltage sources, and then you program them, how you want the voltages to change, if you want to apply harmonics or negative sequence or faults, all those things you can program here to properly do it. Make it unbalanced, balanced, and these things. The controller, there are two separate controllers, one for alpha, one for beta. And then after that, you convert alpha, beta to ABC. PWM, yeah, 3 PWMs, bipolar. And this is the current limiting part that uses and reference generation that uses SDP and SQP. And for reference, you use the voltage magnitude. So you have P set, you divide it by VGP to generate ID, and also Q set divided by VGP to find IQ. You limit IDQ and then multiply into SDP, SQP, subtract, and it gives you the reference. And this SDP, SQP come from the PLL. So really the big part here is the PLL, the three-phase, which has positive sequence part, negative sequence part, and the DC part. See? So that's the positive sequence part, has mu1, mu1, mu2, mu1, mu1. The frequency, you don't have to estimate it again. Once you estimate the frequency in the positive sequence, you add it to the negative part. Okay, I think it's quite clear. Let me see if it runs. Okay. So the same performance that I showed you in the figure, you will see here the current, actual current, and the grid voltage here are shown together, 0.1 of the grid voltage. And these are the real and reactive power values, and so on. Okay, so what time is it? 11:46. Maybe we can spend a few minutes for questions if you have. Otherwise, we can leave. Is there any important question anybody wants to ask? Yes, go ahead. Say it again. Ah, sure. Which figure? 7.7.6. Okay. This one. All right. Yeah. Yeah. Well, these two units work together, I agree. The dynamics impact each other, but whether this impact is in a negative direction, is a, impacting the I don't agree that putting this together, it will slow down. Because to be honest, not particularly for this one, but for single phase, we have tested many different scenarios. And in single phase, we come across that this is the best scenario in terms of making a trade-off between speed, this interaction between the loops and everything. So what do you suggest? Uh-huh. Yeah. We can test it, yeah. We can test it. Yeah. Right. Yeah, linear time periodic LTP, right? LTP analysis. Sometimes it's useful. Uh, I have seen that, and I have seen some of the analysis that people have done using that. But I was never convinced that, at least in the context of PLL, it can give us any more information, to be honest. There are a couple of papers which are original in LTP for PLLs. They give really the boundaries of stability for PLL. But those boundaries, and I have published in one of my recent papers, I can show it to you, those boundaries are so away from the region that we are working that they do not really come into picture. There is one paper based on that LTP I recently saw a few years ago, and then I published a paper in response to that paper. So it actually showed the boundaries of the stability and showed that how the PLLs become unstable when you go to that boundary. But it did not mention that those boundaries are not applicable. We never, anybody with sound mind would choose its parameters close to those boundaries. It did not mention that. So for that reason, and because they had mentioned my papers, so I had to write a response, and I did, and I've published. If you like, you can read that paper. Here, these are the simulations that actually accompanied my book, and I had my reasons to include continuous time domain simulations, not discrete time domain, for the sake of practicality and academic approach. But all the simulations that are relevant and we have used in our papers, technical papers, we have done in digital, and then we have implemented in the lab, right? So I'm using these simulations because you will receive a copy of these materials, which are the textbook materials, right? But yes, we have, for all of them, we have them. But my experience, I'm going to tell you, if you do a good, correct simulation in continuous time, compared to digital time, the only thing that you are missing is that one sample delay. And then you can always go back to your simulation, and after your continuous time controller, put one sample transport delay. So this is, I would say, chiefly equivalent to a digital control. If your simulation runs with one sample delay, 1.5 sample delay, in continuous time with no problem, it will run in digital without problem. Yeah, these are problems common to every digital implementation. Fixed point, if you are using fixed point FPGA implementation, you have to watch for the word lengths. Yeah, this is not really our concern here in this course, but any digital implementation for any controller should actually watch all those. 7.18. Yes. Say it again. Oh, this is when it goes to current limiting mode. It cannot transfer that amount of power because the converter limits the current and limits the power. When you limit the current, you cannot supply that amount of power. This power, if it's a capacitor, it goes to that capacitor, or if it's a battery, it will go to that battery. So whenever you limit the current, you have to deviate from the set point. Yeah, it's, but you limit. In other words, set point is given. Set point is given based on the fact that it's normal operation. It didn't know that a fault can happen. So if it's normal operation, it says, I would like to feed 10 kilowatt to this grid as far as everything is normal. But now the grid voltage drops like 50%, right? So if I want to still supply 10 kilowatt to the grid, my current will be 80 amperes. However, the switch can only tolerate 70 amperes. So I have to clip the current. So the power goes down. That's basic. So let's start in 12:05 if it's not too tight, so we can hopefully finish before 1.